Yesterday, I coded for 3.5 hours. Well, I worked with the interlocutor on some code. Okay, and that's how I spent this time segment. I was still studying. You don't get time off. Because I didn't take time off. It's snowing dust in here. I'm not sure what it's coming off of either. Well, anyway. I could bring the air filter thing over here. And blast us with white noise. Let's see. Yeah, we'll clean this one just for the sake of not running over onto the next page. Alright. Yeah. Flipped a coin. Lost the coin flip. Yeah, let me see here. Use of the variables r and s in the last two theorems is no formal innovation, for all capital italic letters are set variables. It is meant to be merely suggestive. It's like a comment, a little bit of code in the comments section. It is meant to be merely suggestive of the fact that we are intuitively thinking about those sets which are relations, although the theorems hold for arbitrary sets. I'm not sure what it means for these theorems to hold for arbitrary sets. I mean, this might be saying R intersection S, then R intersection S. But then that wouldn't work for union. If it's saying R and S are sets, then R intersection S is a set. If R is a relation, then the domain of R in symbols domain of R is the set of all things X such that for some Y, the ordered pair XY is an element of R. Thus, if R1 is equal to the set containing these elements, the ordered pairs 0, 1, and 2, 3, then the domain of R is equal to the set containing these elements 0, 2. The range of R in symbols cursive R of R is the set of all things Y such that for some X, the ordered pair XY is an element of R. Thus, the cursive R of R1 is equal to the set containing these elements 1, 3. The range of a relation is also called the counter domain or converse domain. The field of a relation in symbols cursive F of R is the union of its domain and range. For example, F cursive F of R1 here is 0, 1, 2, 3. In the obvious formal developments connected with the three concepts of domain, range, and field, the only difficult problem is to show that the intuitively appropriate set exists. As usual, the definitions themselves are axiom-free. Okay. We have definition 3. The domain of a, I'll put that in parens, though the author does not, is equal to the set containing its elements X such that there exists a y such that x may y. Okay. That the domain of A is the appropriate set is confirmed by the following theorem. Apparently we're going to need the axiom schema of separation. Let me see here. Theorem 4. Yeah, I think the author has a lengthier proof here, but I think we're willing just to say like if I say so like we could say x is an element of A, or hold on, so A is equal to B. Okay. What is this dust? Okay. Actually, I think I'll probably get away with just having the absurd amount of dust. I'm not sure what I've done that has kicked up this dust. Let's see. So now if I say yeah, so this coloring scheme we have is a kind of meta logic in a way. Well, I don't know if I'd call it meta logic, but it's something interesting. What do I mean? Let's see. So I say there's your x, and there's your x again. Okay, and then I say there's your s, and there's your s again. Alright, and then I say there's your phi, there's your phi again. Okay, and then I say, let's see, x is an element of the set containing as elements s such that there exists a y such that s a y. Right. And now there's your x. Okay. There's your s. Okay. There's your s. Well, what can this be? Incidentally, this is okay. Hold on. Let's see. This whole thing is phi, and then incidentally we'll do like green for y, and then Okay. Now, if and only if. Well, what is the phi expression? So then we'd say xay. So there exists a y such that x a y. Okay. Now what? Now, so this is once again our phi expression. Okay. And then there's a. Why, in so many other cases, when we make things, in so many other cases, we make things so much more difficult to prove, to work with, why am I willing to trust a color template just immediately? Because this is a statement about my substitution willingness. This isn't a statement about math objects, as it were. It's a statement about what statements I'm willing to construct. Maybe that's my point here. Okay. I don't have anything better to go by than a coloring template for these expressions. So, I mean, given that this is the substitution rule that I'm going to follow, this had as well be a definition, I guess. Okay, but what falls out of this expression? I'm not sure yet. Well, but then this was the proof, right? Now, I guess that's proof enough then. Yep. The author, in this case, the author has to go to much more efforts than I do because this doesn't bother me, but it does bother the author. So I guess we'll read why it bothers the author. First, though, what is this expression telling me? We can always step down an interderivable into a direct yes, actually, that relationship is only one direction, so we might make a logical framing point here. case of goldenrods. I need a case of goldenrod colored pencils. I think you can actually order individuals if you so desire. Let's see here. A little box in the air. Interesting, interesting. And yes, I want to note that that relationship is one way. Why, as evidence, as commentary, I would note that if I have A then B and B then A. Alright. Now, but these are atomic. Well, yeah, so it would... It's like we want another layer of cursivity. A layer of cursivity, where we could say if these letters were cursive, they would be metavariables. I mean, I can't do anything with A then B, nor can I do anything with B then A. Well, I can transform them logically. I can do not or. Supposing I give myself that logical operator or logical transformation, I can make this not or. But I can't logically derive, unless I can logically derive A from B. But in this case, A and B are merely set variables. So really the better statement would be P then Q. Yes, which we specifically don't use even though they are granted to us as set variables. So now if I say P if and only if Q is interderivable with the expression P then Q and Q then P. Okay. However, I can't. These are not derivables. Okay, I guess I would say it must be granted. But that's, again, a logic point. That isn't a point specifically about set theory. Well, so the point, I get, maybe the point would be in an actual proof, you'd be given something like yeah, well, you'd be given X is an element of A, then X is... well, if you say, like, if A is a subset of B, then... Or A is a subset of B if and only if... Okay, I can't derive that A is a subset of B. Well, as an example of this... is a subset of B, then A intersection B is equal to A. Okay, and now the point here is that, okay, this is a quote. It's also a theorem that we had to prove earlier. Now, if I say A is equal to the set containing its elements 1, 2, and I say that B is equal to the set containing its elements 1, 2, 3, then I say meaningless gibberish. Doesn't mean anything. Doesn't mean anything. Okay, if I want to talk about the motivations behind these theorems, I might construct these to draw examples, but this doesn't have any technical weight. Doesn't have any mechanical weight. It would be like we have an oracle where we have an oracle that can look at these sets and give us this status. Okay, and now I can't derive this, but supposing there were some entity that could tell us this. Rather, so I can't derive this might be biconditional, incidentally. But so I can't derive that A is a subset of B. Someone would have to tell me this. So that's why I'm saying it's like, so these goldenrod underlines have developed into a way of saying that we can't see what this says, as in a way of speaking. What do I mean? Like, what is the expression R is a relation, as an example? A is a relation. I might as well say P is, if I had a logical variable that I had not yet selected, the next one in line, or a numbering scheme based on page number or definition that I'm on, along with axioms or whatever. Okay, then this would be some schematic name, some generated name, and I'd say generated name is typographically replaceable with, even if not interderivable with, the expression for all x is an element of A, then there exists a y, there exists a z, such that x is equal to the ordered pair yz. And now for convenience, I offer a label, A is a relation, but that's never going to become relevant. We don't have to know that that's the label in order to perform this, or to use this logical relation. Well, practical relation, I guess, where I'm talking about interderivability, typographical replaceability. Okay, now, in general, I'm saying, and this might be what our use of this color stabilizes into. This is a label. We can't see what it says. Well, you and I can secretly, but the person writing in the notebook, as it were, can't see what this says. And now, the empty set is a relation. This would be like saying tau of phi. That's Q. Hold on. Tau of the empty set, rather. E.g. just some operator. Operator of the empty set. It's a Boolean, it's an oracle. It's a Boolean generator. I wrap the empty set in a Boolean generator and it returns true. I wrap the empty set in this Boolean generator and it returns true. Or if I know that this is true about A and then I wrap A in the Boolean generator, then the Boolean generator generates true instead of false. And vice versa. If I somehow had the Boolean generator and I could wrap it around A, then I would know that this statement holds. And it's the Boolean generator that has the sticker on it that says P125Q. Okay. Now, similarly, I can't see this, and what that practically means is that I can't. This has no proof weight. In this context, I'm pointing out that this statement A is a subset of B would have to fall out of a Boolean generator. Like if I had subset A comma B yields hashtag true. Okay. Or if yes, okay, so the Boolean generator of this kind, if it yields true, then, well, if and only if. Yeah, the tick mark doesn't make any sense in this context, I'm afraid. Yeah, none of the other options make so much sense either. Oh, blank spot. Let's see. So this is gesturing towards the idea, if I have this already, if this falls out of something else I know, then if I were to pass A and B through the Boolean generator, I would get back true. If I put A and B in the Boolean generator and I get back true, then I know that for all x is an element of A, then x is an element of B. Okay, and now what relation does that have to the above observation? Right, so we get back to this observation. So this started by saying that if I have the crosshatched biconditional between A and B, then I can step that down into the expression A if and only if B. And well, that's akin to saying that let me think here. It's akin to saying that if A is interderivable with B, then this statement can't be false. The uncrosshatched biconditional, the mere logical manipulation can't be false. Which is in turn a way of observing, let's see. So if I say A is a subset of B, if and only if let's see, for all x is an element of A, then x is an element of B. Right, and then I wrap that, and I say A is a subset of B biconditional. Yeah, I want to use color with that. If for all x is an element of A, dot, dot, dot. prove that. Okay, if A is a subset of B, then for all x, phi of x, and if phi of x okay. And now this will work out, as it turns out. This is now interderivable with not x is an element of A for all x. Okay, yeah, we can do that over here. For all x, not x is an element of A, or x is an element of B. Or for all x, phi of x. Okay. And what are our quantifiers doing here? Yeah, I think we might have cheated with our quantifiers. Rushing, yeah. So this should say, well, so this would have passed to not A as a subset of B, and then that would be not for all x. Similarly, we're going to get that negation over here with the phi of x expression. So this would be not for all of x, and then it would pass through, so there exists an x such that not. Okay. And there exists an x such that not phi of x or for all x, x is an element of A, and x is an element of B. Okay. Have I confused myself needlessly? Let's see. Yes, that was a loss of time as a result of not writing out the intermediate step. Let me see here. Yeah, we have to figure out what 5x is. What did what did I put in place for 5x? Let's see. Oh, I see. Hold on. Yes, this is not a very good proof, is it? Because it's starting with knowledge of starting with the mechanical ability simply to perform the transformation. We're already stepping between A is a subset of B, and for all x, x is an element of A, then x is an element of B. Okay, but then that's also the point here, right? Yes, I confused myself. Let me think. The point is that, well, if the point is merely that if I give myself the substitution rule that's stated in the theorem, then I can perform the substitution, then that's not such an illuminating point, maybe. Yeah, okay. We'll bail out of this point. Well, so the problem with choosing this as an example is that this is one of the goldenrod. I'll make that note. A is a subset of B. It's also one of these goldenrod expressions. Okay, what do I want to get out of these goldenrod observations? So I can't see an expression like this until we're doing an example, and then we step out of the technique and use examples like this freely. And then A if and only if B. Right, so P biconditional Q is interderivable with the expression P then Q and Q then P. Okay, which is in turn interderivable if we grant it with not P or Q and not Q or P. But the point that we're making here is that we would have to be given these two expressions. The expression P then Q, aside from its mechanical transformations, is opaque. I can't derive its truth from the ground. Okay. And what is the relationship between that observation and here? So I'm saying I can step down any interderivability expression with a biconditional expression into a biconditional expression. Well, and in the case of these goldenrod expressions, that ends up merely being the observation that, given the typographical rules that I have accrued, let me see here. If I'm willing to perform any of the typographical transformations I've already given myself, then this assertion tells me, if I have this interderivability expression, I know that I have the typographical rule necessary to give myself A if and only if B. Because this would be saying, well, it would be akin to saying A interderivable B step down to saying effectively C if and only if C. Okay. Now, so when I say for all x is an element of the domain of A is interderivable with the expression there exists a y such that x a y. I'm not sure. Okay, let's go to the next. Well, no, so let's do for all x is an element of the domain of A is interderivable with the expression there exists a y such that x a y. Okay. So, if there exists an x and there exists a y, such that the ordered pair x, y is an element of A. I guess what we're wanting to say is that there's a y such that the set containing as elements x, and the set containing as elements x, y is an element of A. Huh. Not sure what point I'm making. Let's see. I spent about 30 minutes earlier reading the start to Theorem Proving Lean. My duster has become too dusty. That's a problem for the dust buildup. Hold on. Right, well, thought strikes me to give up on calculus. For now. It's kind of a vanity project. Well, it's establishing mathematical maturity, though this is doing the same, I guess. Let me see here. That the domain of A is the appropriate set is confirmed by the following theorem. Okay, the author starts with what is plain and obvious nonsense in this context, which is always a good sign. Let me see. What do I mean? We start by saying there exists a B such that for all x, x is an element of B biconditional x is an element of the big union of the big union of A, and there exists a y such that x a y. Okay. What could the relevance of this possibly be? Unclear. Let's store some of these quantifiers. Shall we? Okay, let's see. I don't really remember how the axiom schema of separation is used. Not X is an element of B, or X is an element. Let's see. Yeah, there exists a set C such that X is an element of C and C is an element of A. And there exists a Y such that the ordered pair X, Y is an element of A. Okay. These brackets are kind of horrible. Yeah, let me actually keep the biconditional for now. In fact, we'll store this, and we will move forward. Okay, so what do we want to do with the right-hand side of this? There exists a C such that X is an element of C and C is an element. No, this is wrong. Pink. C is an element of the big union of A. Okay, glad we clarified that. We double bracketed. Yeah, I don't think we need the double bracket. Alright, we'll say, and there exists a Y such that the ordered pair X, Y is an element of A. But actually I want to say the set containing its elements X. Do I wanna? One question here would be, why don't I wrap this in goldenrod in an unintelligibility wrapper? Why is that an intelligible expression? I don't think it is, but well, actually, it's interesting that this keeps splitting our set theory in a, I don't know, like an amenable manner. What do I mean? Well, am I willing to accept the domain as an argument. I'm not it doesn't require us to talk about individuals, which would be an objection here. Sort of arbitrary objection, admittedly, but one that we're nevertheless maintaining. Don't really want to talk about individuals. Let's just keep expanding this. So we're going to say there exists a C such that X is an element of C, and there exists a D such that C is an element of D, and D is an element of A. Yeah, I'm not keen on stepping down the biconditional here because we need the biconditional, don't we? Let me see. Kind of losing track of what we're trying to accomplish here. Hmm. Well, I mean, we could make this really horrible. We could say there exists a C such that the set containing its elements X is an element of C, and the set containing its elements X, Y is an element of C, and for all capital S, if capital S is not equal to the set containing its elements X, and S is not equal to the set containing its elements X, Y, then not S is an element of the big union of A. No, rather it's not an element of C. Right. We missed. Yeah, though we're also running out of room. We're gonna have to split these up. And C is an element of A critically. Okay, from which we can get, let's see. From which we can get there exists a C such that most critically, we're going to underline that. So, let's see. And now, if nothing else, we would want this dark green expression and this expression combined to give us that the big union of A. Let me think here. Yeah, we needed another shade of green. Let's see. I think it was a mistake to use red here. Then declare it a mistake. Well, the point of using it here was to say this expression. Alright, I'm gonna stand up, walk around. I guess we have to make a decision soon what we're gonna do with calculus. Yes, so the idea would be we're studying calculus as a lead-in to something like linear algebra. And then thence to abstract algebra. Okay, with the observation here that we could probably, if we finished axiomatic set theory, then maybe we don't need to do calculus before linear algebra. Maybe. Well, so the question is, I suppose, like this I take to be a kind of, as it were, detailed, desaturated form of working through calculus, working through analysis. It's really a detailed, desaturated form of working through any kind of math. It's about where you're willing to put symbols. Well, all of math is about where you're willing to put symbols. At least any math that we would be doing in a notebook. And the idea that we give the time over to lean wheel. Well, you know, if someone said, hey, we'll give you a grant, spend 3 more hours a day looking at lean. Well, yeah, it's a good idea. I think I will do that. Wonder if it's illegal to go around at night with dandelion seed. Dandelion that's gone to seed. Blow them in every public park. Better than kale. Dandelion leaves. Dandelion flowers too. Dandelion roots are edible, flowers. Stems are probably edible. Roots aerate the soil, draw up nutrients because the tap roots go really deep. Just go around saturating every park with dandelion seed. Turn them into dandelion farms. Oh, but it'll kill the grass. And now the point would be, we could oversaturate the ability of the local government to remove all the dandelions. There is a finite capacity. There's a finite number of landscapers in the region. And the question is, can I blow so many dandelion seeds into the ground, into the parks, that I can overwhelm the landscaping ability? You have to import, to recruit landscapers from the tri-state area. Well, and the point is you do it all at once, right? And if they can't solve the problem fast enough, they might not even realize it is a problem until it's too late. If all the dandelions I plant go to seed, it will be impossible to get them all. To say, restaurants, we need you to start serving dandelion salads. We have to get some money flowing into the dandelion removal activity. Local coffee shops, we're going to teach you about dandelion root coffee, and you're going to start selling it. If this doesn't become a commercial activity, it will be impossible to deal with. Will have to be this clandestine activity. I'll have to gather. What if I told you I had 3 crates, big crates, filled with dandelions I gathered over the course of roughly 5 years? open those crates with a portable fan. I don't know how long dandelion seeds remain viable. Staging grounds outside the city limits. Buy a cheap plot of land. Make it a dandelion farm. Gather up seeds after I've saturated my own plot of land. Dandelions. Now, I think there's also dandelion latex, actually. Forgot to put the knee brace on. Hopefully that doesn't come back to punish me. Skipping out on calculus. We will do calculus. Alright, let's see. $334. In reality, the overall population is most likely increasing or decreasing throughout each year. Uh-huh. Oh, from the previous problem. Okay, not on Earth. If you take a small enough time interval, I suppose the population on Earth would be decreasing. In reality, the overall population is most likely increasing or decreasing throughout each year. Let's reformulate the model as P of t is equal to 82.5 minus 67.5 times the cosine of pi divided by 6 t plus t. Okay, if you say so. Where t is time in months, 0 represents January 1st, and p is population in thousands. When is the first time that the population increases 200,000? Reaches 200,000, rather. Okay, so this is when this is equal to 200. Okay. Well, we can start by calculate. You know, actually, if I had my pocket calculator, it strikes me that would be a better option than using my computer. In fact, let me look into that briefly. Alright, I do still have my graphing calculator from back in the day. However, I need batteries for it. So, I guess I'll get that soon. Alright, now, calculator. With my computer, 200, minus 82.5, 117.5. Probably didn't need a calculator, no, but 117.5 is equal to negative 67.5 times the cosine of pi divided by 6t plus t. Interesting. Well, so we could do, so no, we don't have such a formula. Huh. Now there's an approximation point, which is that if I instead say 67, well, I could say cosine of phi uh, 117.5 divided by 67.5. Yeah, okay. 1.741. Well, actually, 1.740 repeating. Okay. now we claim that this term is negligible. Because it maxes out at 12, and we're dividing by 67. Would be the claim, yeah. Yeah, well, it does us no good to have phi is equal to the cosine inverse of t minus 117.5 divided by 67 divided by here. That'd be positive divided by 67.5. Which is equal to t pi divided by 6. But again, does me no good because I have t in both of these expressions. Though it might make this more tractable. So we're saying that t is equal to the cosine inverse 6 times the cosine inverse of t minus 117.5 divided by 67.5. Okay, all divided by pi. Interesting. And so the idea is that, well, now we can just create a table of values. A is equal to the set containing as elements 0, 1, dot, 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 12. And B is equal to the set containing as elements phi of 0. Well, let me go over to Racket. Not lean, the mathematics language? Nope, not yet anyway. right, so let me see. /list I is range 13. Okay, we're gonna do *6 ACOS, which might be right, but also might not be right. Minus I 117.5 divide minus I 117.5 67.5 divide, and this will be pi. Who knows what requirements we will have to make here. Okay, run. Ah, it just works. It just works. Yeah, these are all complex numbers. Why are they complex numbers? It's not, for instance, because I made this. No, surely not. But just as a matter of principle, we'll go ahead and do that. Now, okay, why are these numbers imaginary? It has something to do with taking the arc cosine of this negative number, but it... Yeah, okay, so we have to translate that into... We would have to translate this value into a corresponding... Okay, so let me... this value inside the arc cosine. So let's make an easier set. /list j range 13 divide minus j 117.5 67.5. Okay, and actually let's do const j. Okay. So now these are the values here. Okay. And now I'm going to say f of x is equal to t minus 117.5 divided by 67.5. Okay. Now what is the idea? Now, this is, right, so we're saying f of a is equal to the set containing its elements. Yeah, and then it's this list of bare particulars. Okay, and now what are we supposed to do with these bare particulars? We want to map them. we want their corresponding values. Okay, so let's see. The idea here being so negative 1.740 is equal to negative pi divided by a. Negative 1.563 is equal to negative pi divided by b. Okay, a is equal to actually it would just be positive pi. I mean, we end up finding out the value that we want either way, but a is equal to pi divided by negative 1.740. Okay, and b is equal to pi divided by negative 1.563. Okay, and what are these values? Divide pi negative 1.740 and divide pi negative 1.563. Alright, so a is going to be equal to, yeah, that's not so useful, is it? No. Doesn't really lend itself to what we're trying to figure out here. What do I mean? Well, I mean, this is going to be a larger value than pi divided by 2, e.g. Right. So let's do /list j range 13. Well, yeah, this isn't going to be range 13. Let me think. Yeah, we could do 12s and then pi. So, well, then it would still be range 13, actually, conveniently. Okay, yeah. But that's a coincidence. It's not because of the months. So we're going to do /list, which is going to construct a list. We're going to const the value of j just for record keeping. And we're going to do divide star j pi 12. Okay. And what is that going to tell us? That is going to tell us that intriguing. So pi halves is effectively, yeah, okay, so, yeah, this is merely telling us the decimalized values for the pi divided by 12 positions, which is finer grained than the typical special angles, but since we're getting a computer involved, we're free to do as we please on that front. Okay, so what is this telling me? Alright, so we're going to have, let me see here, 6 pi halves, nope, 6 pi 12s rather, is equal to, well, okay, let's just make that its own set. So A is equal to the set containing as elements pi divided by 12, 2 pi divided by 12, comma dot dot dot, 12 pi Well then, so we specifically want these critical values, so 6 pi divided by 12. But then before that, we want, well, somewhere between 6 and 7, apparently. Yeah, okay, we'll do 6 and 7. Is 1.57. Oops. You're not at that stage of the record keeping yet. And then 7 pi divided by 12, comma, dot, 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 and then 12 pi divided by 12, though we don't really need the tail end of that. Okay, and now we're going to have b is equal to, well, and then actually this is just a again because we're not performing a transformation. A is equal to point 0.262, comma, dot, dot, dot. We're just going to skip that one, alright, because we don't need it. Alright, so red. This will be, I guess, green, and then white. Alright, so we skip straight to green. 6 pi is 1.57, 1, then 7 pi, 1.833, comma, dot, 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 comma, and then 3.14. Well, yeah, pi. Okay. Now, what is the idea? So this is giving us let me see. Well, so if nothing else, this is telling us that pi divided by 12 is, rather 6 pi divided by 12 is equal to this roughly. So if I say 1.57 is equal to pi divided by b, then b is equal to 2, okay? And if I say that negative 1.57 is equal to pi divided by b, then b is equal to negative 2. Okay, I don't think that's the... Well, okay, yeah. So what that's trying to tell me is that... Why do I care about this value, incidentally? Because, yeah, we probably need to color this a little bit more effectively, and I need to stay a little bit more focused, because this chain of reasoning is gonna go a little bit long. So we have a is equal to the set containing these elements 0, 1 through 12. F of x is this subfunction that's inside the arc cosine. So the motivation for this is to say cosine inverse of f of x. we're saying after we pass these x values, 0 through 12 through f of a, we obtain these values. The range of negative 1.74 to negative 1.74 to negative 1.56. Okay. Now we're noting that that corresponds down here to roughly there. That's going to be negative 1.57. Okay, now the cosine value there is going to correspond to up here, 1.57. Same cosine value. And now the idea is that so if we had 7 pi 12s, yeah, we'll just claim that that's equal for convenience. So alright, and now the idea is that somewhere over here we have I should just, yeah, whatever. So that's going to be 1.83. Alright, and then somewhere in between is going to be okay, though the follow-up observation well, actually, so if I instead assign these to yeah, okay, that's an idea. I'll give this dark green. Alright, and now I assign 1.74 to this green. Okay. Now this will be 1.74. Okay, and now alright, so the idea is that, yeah, though the presentation's off, but the idea is that this constitutes an interval within which, yes, well, every value in here, this is monotonically increasing in value. So how do we make all of this come together? Let's see here. A is equal to the set containing its elements 1, 2, ... through 12. F of x is equal to t minus 117.5 divided by 67.5. Alright. Now f applied to a, I don't know if that's what you'd write, I don't know if that's what you'd write, but whatever. F applied to a gives me the set containing its elements negative 1.74, negative 1.73, comma, negative 1.56. Okay. Yes, okay. And now we say B, I'm going to say C. I'm going to skip over the honorary B position. C is equal to the set containing as elements pi 12s. Why pick 12s? Yeah. It's not good enough for... Yeah, it just falls out of pi 6th, but yeah, we'd have to do pi 24ths. Yeah, though it's also nonsense values, right? Pi divided by 12, 2 pi divided by 12. We're off in Wonderland with these values. Dot dot dot. Comma 6 pi divided by 12, comma, and here's the real innovation. 5 pi divided by 12, comma, 7 pi divided by 12. Okay, comma, dot dot dot, comma, 12 pi divided by 12. Alright, so now once again, we will label this with red. Okay, and then we will label this with violet. Now, yeah, okay. Where phi is an element of the gibberish set, what we know about it is that it is between the values of 6 and 7. Alright. 6 is less than 7. 6 is less than phi is less than 7. Comma, phi is an element of the gibberish set. Alright. Then what? Then we're going to say that, right, so the idea, if we go back to this function, let me think here. Right, so this is dividing j times pi by 12, where j is any value in the range from 1 to 12, inclusive. Alright, if it is 6 pi divided by 12, we get 1.57, which is a close match to our 1.56. Alright, so 6 pi divided by 12 is equal to 1.57. Which is less than 5 pi divided by 12, which is equal to 1.740. Actually, as it turns out, this is an element of the rationals, but some of the rational values are also elements of the gibberish set. Like this one, yes. And then we have 7 pi. Which is equal to 1.83. Alright, then what? Then we note that for all x, if x is an element of f of a, then roughly, we will have x, yeah, hold on, that's wrong notation, let's see. 1.57 is roughly less than x, which is less than 1.74. Okay. With some suitable compensation for the fact that these are positive values instead of negative values. Say f is an element of negative f of a. Alright. Now what is the idea? So the idea is that if I have a number line, over here we have 1.57, over here we have 1.74. Okay. And then we don't have 1,000 shades of green, if only, but okay. And now correspondingly, yeah, we can do that. Let's see. Right. Okay. And what that gives me is that, let's see. So all of the values in f of a, f applied to the set A, all of those values fall between these two positions. And why do I care about that? So cosine, let's underline this with red. Actually, let's do blue. Okay, let's see. Alright, so now I say g of x is equal to the cosine inverse of f of x. Okay. And what do I get out of that? Now I say the maximum value, the maximally negative value Right, well the value would be equal to 0 here. So G of A is equal to the set containing as elements 0, comma, dot, 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 comma, negative the arc cosine of A cos 1.74, which is why would that be an imaginary value? Okay, maybe I shouldn't be using Racket to calculate that. Hold on, let's check the calculator suite. Different calculators are giving you different answers, you say. That's interesting. Let's see. Undefined. Why would that be undefined? The domain of the arc cosine should be from 0 to... Oh, I'm doing this wrong. Oh no. Let's see. These are angles, yeah, and the arc cosine does not take in angles. The cosine takes in angles, yeah. Let me see here. Yeah, okay, but then why isn't that just illegal? What do I mean? Maybe we miscalculated something. Well, let's gracefully say routing error. Alright, now, what do we want to say? Right, so if we start with the function p of t, is equal to 82.5 minus 67.5 times the cosine of, let's make that a bracket, I divided by 6 times t plus t. Okay. Then we're saying 117.5 is equal to negative 67.5 times the cosine of pi t divided by t and then plus t. Okay. And now t is equal to So what we did before is we isolated this expression and took the arc cosine. And the illegality of that activity did not strike us at any point. No. Why would it? well, it's not pi t divided by t, it's just pi t divided by 6, I guess. So that does not seem possible. Why not? Because t maxes out at 12, and this mins out at 117.5. Huh. Which might be the point of the exercise, actually. Let's see. What camera am I on? Okay, let's see. I mean, there's also, yeah, that's a follow-up point. T is a time indicator. Now, I'm perfectly willing to strip all units out and we just only work with numbers. In fact, if we didn't want to work with numbers, but we wanted to work with sets inside of sets, I'd do that too. However, the world seems picky about units, unlike myself. Okay. So I think this is just a disheveled question. Which is good, because we couldn't calculate the answer anyway. But yeah, let's plug it into the calculator now that we've figured out that this is a disheveled question. Let's see, 82.5 minus y. Why does every aspect of this program just... let's see. Pi times x divided by 6 plus x. Where'd the graph go? Huh. And yes, the answer is it never hits 200. Or it was at 200 at negative something months. Okay. Never to be seen again. Wait a minute, where did my cosine operation go? Okay, that is incorrect. Let me see here. All right, now it's a disheveled equation in a sense that t is a time variable. So it has the unit of month. But then if I say that there happens to be an association between the month progressing and the population increasing by 1,000, then there isn't really a problem there. Which is what's represented in this graph. But that isn't the only reason I thought that this was malformed. No, let me think here. And indeed, I think our technique should have, or like, I think we should still be able to find a way to figure out this value. I'm getting a little bit lost here. Let me see. Yeah, well, I'm not understanding what this operation is telling us. P of t is equal to 82.5 minus 67.5 times the cosine of pi divided by 6t plus t. I replace P of t with the value of 200 because that's the question. That's the population in question. Okay, then I subtract, I get 117.5 minus 67.5 times the cosine of this expression plus t. Okay, that's an interesting point, that t is not limited to 12, so our variable is no longer cyclical. Before, we wouldn't have talked about, well, I don't know, maybe we would have, but we weren't thinking about t as if it could extend to a value beyond 12, but actually, as this graph clearly indicates, it can extend beyond 12. Which is convenient because the first case where we get a population of 200 is roughly 58, 50 something, 52, whatever, months in. Let's see if I can have y equals 200, and then a point A. Okay, can you tell me anything about A? 53.39, 53.4. Alright, so if I say 53.4 is equal to 117.5 plus 67.5 times the cosine of... yes, interesting. Now pi divided by, or pi times 53.4 pi. Treat pi like it's a variable. 53.4 pi divided by 6. Okay, and now that's perfectly reasonable because the value for t can increase. But also because, yeah, let's follow through with the inversion, or the arc cosine operation. Let me see here. So we're going to say 67.5 times the cosine of pi t divided by 6 is equal to 117.5. I had this expression up here, t minus 117.5. Okay, and to forego the conclusion here, we're going to say never mind, I don't have the equation on this side. Alright, let's just derive it again. Alright, so pi t divided by 6 is equal to the cosine inverse of t minus 117.5 divided by 67.5. Okay. Semicolon t is equal to 6 times the cosine inverse of t minus 117.5 divided by 6, all divided by pi. Alright, and now what is the idea? We are not restricted to 12. I see. I don't think that's actually supposed to be the takeaway here. Though conveniently, that observation works. What do I mean? So now what we want to find out is so t minus 117.5 divided by 6 is equal to 0. Think here. That's not quite the point, is it? Taking the arc cosine. Right, so negative 1 to 1. Yes, okay, negative 1. And then t minus 117.5 divided by 6 is equal to 0. T minus 117.5 divided by 6 is equal to positive 1. Alright. Now t is equal to 111.5. T is equal to 117.5. And t is equal to... Yeah, so that's not quite the point. Oh, maybe that is quite the point. Yeah, because there's another term here. Or there's a continuation of the expression. This is only giving us the internal content of cosine inverse. So this is going to be equal to 123.5. Okay, now what is the idea? So now 111.5 is equal to 6 times the cosine inverse. We're missing something. Yes, this is all getting out of whack. What time is it? We still have 10 minutes. Okay. What is going wrong here? Oh, well actually, so the cosine inverse is going to give us a value up to Well, that's going to give us a value up to pi, which is not the reassurance that we're looking for, right? Because the expression that we're calculating is, let me see, this should be clearer. Right here. So this maxes out at a value of 1, no, rather at a value of pi. So that would be, well, and then it'd just be t is equal to 6. But that's not right either. There might be a point lingering here, which is that this is what strikes me, though I'm not sure this is the right idea. Here we have A at 53.4. 1236.48. 53.4 minus 48 is 5.4. And the point here is that, let me see. Right, so in this minimal value case, we get -1, and that's the case where this is equal to pi. Okay, so we're saying that lambda of 111.5 is equal to 6. Okay. Lambda of pi halves. Lambda of 117.5 is equal to, so the cosine inverse of 0, which is equal to pi halves. And we would have actually 3. Okay, and now this will be positive, which is equal to 0. Lambda of 123.5 is equal to 0. Okay. And now the fanciful idea is that (53.4) minus 48 is equal to 5.4, semicolon 6 is greater than 5.4, which is greater than 3. So if we could figure out a justification for modding down the value to 5.4, then we have a way of getting that value. But I think this is turning a little bit rough. Okay. Well, we only got 5 minutes left anyway. Alright, I'll see you later.